All right, let's start. From this week till the end of this module, I will take over from Richard. Since you have done your coursework 1, now we can think about coursework 2. So today I will talk about the background and principle behind coursework 2 code, and also I will talk about the requirements for coursework 2. So the coursework 2 is taken from the field called CFD, computational fluid dynamics. Actually, it's similar to the principle of coursework 1. In coursework 1, we kind of model the heat flow, right? So the heat will flow from the high temperature area to the low temperature area. For the CFD, we're trying to model the fluid dynamics. So this modeling is based on 3 physical principles. First is the mass conservation, which means that the amount of fluid flow into an area equals to the amount of fluid flowing out of that area. So the mass is conserved. And the second principle is the Newton's second law, which is F equals to ma. So the applied force equals to the mass times the acceleration that the object can gain. Right? And the third principle is the energy conservation, which means that in a closed area, the total energy is remain conserved, constant. Right? It's just that the energy is transferred from one energy store to another energy store. So these models is expressed as the partial differential equations, right? Which is called the governing equations. If you want to know what these partial differential equations or the governing equations look like, they look like this, right? It's quite complicated. So the first equation represents the mass conservation or mass continuity, right? Mass continuity. And the following 3 equations represent the Newton's second law. So you can see that it's the momentum at the x and y and z dimension. And the final equation is about the energy conservation, right? So you can see that there is a coordinates, which is the coordinates physical locations, right, of the area. And there is a time, and there is a pressure, and there is a velocity. So the independent variables are the coordinates and the time, and the dependent variables are the fluid properties. For example, pressure, velocity, etc. So basically, this governing equations tries to establish the relation between the fluid properties. Right? In our case, we are concerned about the velocity of the fluid and also the pressure of the fluid. So we are trying to calculate the values of the velocity and the pressure of the fluid over the physical locations and also over time. So the physical coordinates and the time are independent variables, and the velocity and the pressure are the dependent variables we are trying to find a solution to. We know that these governing equations are very complicated. They are partial differential equations. So it's extremely difficult, if not impossible, to find or to derive the analytical solutions. So what we can do is to use computers to apply numerical method to find the numerical solutions. Right. So these numerical solutions are the approximation of the exact solutions. They're trying to find the numerical solutions of the fluid properties over physical locations and also over time. Because in a physical area, there is unlimited number of physical locations. So the first thing we need to do is to discretize the physical space. Right? What we do is to discretize, for example, this is a 2D physical area. We discretize it into a number of cells, right? We are not trying to find the solutions over all the physical locations in the area. We just find the numerical solutions for one point of a cell. Normally, it's the center point of a cell, right? So we only need to find solutions to a grid of discrete points in the area. Right? Similar for the time, because there is an unlimited number of time points in the time duration. So we are going to discretize the time as well. We only calculate the solution of a set of discrete time points. Right? So that's the idea. Now, the code in the coursework is called common. It calculates the velocity and the pressure of a 2D flow. So our code is simpler in the partial differential equations I just showed you, which actually tries to model the 3D fluid flow. The code, when you run the code, it will generate the output. The output basically contains the solutions, but the output is a binary file, so it's not human readable. But we provide the comment to convert these binary files into an image file. Right. Then we can use any image viewer to view the image file or to visualize the image file. So the picture on the top is an example of such an output. So basically, we use the grayscale to represent the speed of the fluid. So the darker the area, it means that the lower the speed is. And the green blob in the middle represents an obstacle in the area. So it's like there is a big rock in the middle of the pond. So the fluid needs to flow around the obstacle. Right? Obviously, the code currently is sequential. Your aim is to parallelize the sequential code, right? Using MPI and also using OpenMP. So we discretize a 2D space into a grid of cells, and the outermost cells are called boundary strip, which basically is the border of the space, right? They are not fluid. And there is a very important concept which is called communication pattern, which means that in order to calculate the solution for one point, for example, this black point, it needs to get how it should communicate with neighboring cells. Right. So this is called communication pattern, which means that in order to calculate this black point, in this case, in our case, it needs to get the data from 4 neighboring points. Right. So this is the communication pattern. So this is the problem we are facing. We have a 2D area, and we discretize the area into a grid of cells. And there are 2 types of cells, fluid and obstacle. Right? CF means fluid, CB means obstacle. And the number of cells in the I dimension is I max. The number of cells in the J dimension is J max. Right? And the outermost cells are the boundary strips. And they are regarded as the obstacle. And there could be obstacle in the middle of the fluid. Right? And the fluid cannot flow through the obstacle cells, right? Has to flow around it. So this is the problem we are facing. We're trying to find the numerical solutions, i.e. the velocity and the pressure at each cell. Right? When I say find the solutions at each cell, I mean find the solution at a point in a cell. Right? We only find the solution for one point at a cell, and we use the velocity and the pressure of that point to represent all the points in that cell. So that's why it's an approximation. Right? And you can imagine the smaller the cell is, the more accurate the approximation is. So for a cell, there are four properties: x dimension velocity, y dimension velocity, pressure, and the cell type. And we have a communication pattern as well. In order to calculate 1 point in this code, it needs to get data from 4 neighboring points. And we call it a 5-point stencil, right? Because there are 4 neighboring points plus the point itself. So we use a stencil of points to calculate the solution for a point. We said that we are going to use the numerical method to find the numerical solutions to the governing equations. So let's look at what's the general steps in a numerical method. Actually, the idea is very simple. We just first generate the initial solution for each cell. Then we check whether the current solution satisfies the governing equations. If they are, okay, we find the satisfactory solution. If they are not, then we generate new solutions based on the current solutions. Then we check again to see that whether the new solutions satisfies the governing equations. Right? So you can see that we need to go through a number of iterations until we can find the correct solutions. So the iterations goes on until we find the satisfactory solution or the termination condition is met. Usually it means that we have reached the maximum number of iterations. We still cannot find satisfactory solution, right? Which means that the solutions do not converge. Right, now let's look at the steps of numerical methods more formally. So this is the RM. We want to find the numerical solution for these linear equation sets. We use this kind of matrix form to represent linear equation sets, right? Because if we have a linear equation set, a very simple linear equation set, we have A11 x1 plus A12 x2 equals to B1, and we have A21 x1 plus A22 x2 equals to B2, right? So this is the linear equation set. And then it can be transformed to a matrix form, right? So A is a coefficient matrix. A basically equals to A11, so this is this A11, and A12, and A21, and A22. Right. Phi is the unknown variable we want to solve. It's a vector of unknown variable we want to solve, which is x1 and x2. And B is called constant vector. It's a vector of constant. In this case, is B1 and P2. Right. So we can use this very concise matrix form to represent a set of linear equations, right? So we want to find the numerical solution for these linear equation sets. The first step, we just generate an initial solution for phi. We call it phi 0. And then we check whether the current solution satisfies this equation, right? This equation sets. Assume that we are at iteration k, right? The current solution is phi, we are at the iteration I. The current solution is phi I. And then we check whether phi I satisfies the governing equation, which is the linear equation set. By the way, we said that the governing equation is the partial differential equations. Why do we want to solve the linear equations? The reason is because in order to find the numerical solution, we need to first transform the partial differential equation to the linear equation sets. Right? For example, in coursework 1, I think we have studied to use a finite difference method to convert the partial differential equations to the linear equations. Right? There are other methods as well. For example, finite volume method. Right? There are different methods to convert partial differential equations to the linear equations. Now assume that the current solution is phi I, and then we check whether the current solution satisfies the governing equation. We just calculate the residue, which is the difference between B and phi A times phi I. Right? If the residue is less than a predefined threshold, we think that the solution is accurate enough. We just swap, saying that we find the correct solution. Otherwise, we use the current solution, phi I, to generate a new solution, which is the solution at iteration I plus 1. Right. Now, f is very important. F is a function we defined to generate new solutions. Right. We can define different ways. We can define different functions. A very simple way is this. Right. So we just use a current solution phi I plus the residue, and we obtain the new solutions. You can imagine f function is very important. With a good function f, maybe the new solutions will approach the final correct solutions very quickly, which means that the process will converge very fast. With a poor function f, maybe the new solutions converge very slow or does not converge at all. Right? So f is very important. So this leads us to SOR, successive over relaxation. Actually, SOR is a method to generate new solutions based on the current solution. Right? So it has been proven that it can speed up the convergence. So we have linear equation sets, A times phi equals to B, and we divide this coefficient matrix into 3 parts. So there is a diagonal D. Right? There is a L, which is a lower part, or called strictly lower triangle, and there is a U, which is a strictly upper triangle. Right? Then SOR defines a function to generate new solutions. So phi k is the current solution. Phi k plus 1 is the new solution. Right? And the DLU are the DLU here. And omega is very important parameter. If value of omega is said to be greater than 1, it can speed up the convergence of a slow converging process. If the value of omega is said to be less than 1, then it can help establish the convergence of a non-converging process. Actually, SOR is used in our code to generate new solutions. Right? So now you know that SOR, right, although the name sounds fancy, but it's just a method or function to generate new solutions. Now let's look at how SOR can be implemented. Right? The original implementation of SOR is like this. Right? We assume that we want to generate a new solution of cell ij. Ij is the index of a cell. Right? For example, this cell. It needs to take 3 inputs. The first is the current solution of 4 neighboring cells. Right? And it needs to know the new solution of its left neighbor. and also the new solution of its top neighbor. Right. If we express this mathematically, it means that assume that we are at the iteration k, right? So pk is the current solution. It needs to take current solution, and also it needs to take the new solution of its left neighbor, which is I minus 1j, and its top neighbor, which is I j minus 1, right, in order to calculate the new solution of cell ij. This introduces a chain of dependency, which means that in order to calculate a new solution of this cell, it needs to know the new solution of these two cells. Right. Let's take this cell as an example. In order to know the new solution of these cells, it needs to know the new solution of these two cells. So it introduces a chain of dependencies. This is fine if we run the code in sequence, because we can just run it from the top left corner. We first calculate the new solution of this cell, and then we can calculate the new solutions of these two cells, right? And then it goes on, right? It goes on. So you can see that this kind of approach forms a wavefront. It's like you throw a stone at the corner of a pond. It will generate a wave. The wave will spread across the pond. Right? This kind of wavefront application is notoriously bad for parallelization. The reason is because there is a dependency between different steps. Right? So we cannot start step 2 until we have finished step 1. We cannot start step 3 until we have finished step 2. So we cannot parallelize different steps. The only thing we can parallelize is to parallelize the execution or parallelize the calculation of the cells in the same step. Right. For example, in the step 3, we can parallelize or we can calculate the solution of these 3 cells in parallel. But the problem is that you can see that in different steps, the number of cells is different, right? Which means that the workload is not balanced in different steps. So this is not good. It means that some resources may be just idle in the early stage of the calculation. Right. So the reason wavefront application is not good for parallelization is because there is a chain of dependency, and the workload is not balanced in different steps. Right. Now, the researchers developed a new implementation for SOR. It's called the red-black SOR. It divides the cells into 2 groups, red group and black group. Right. A red cell is surrounded by 4 black cells, and vice versa. Now, if we want to calculate, we first calculate the new solutions of red cells. Right. The new solutions of red cells now only depends on the current solution of the 4 neighboring cells, which are black cells, because we already know the current solution of the cells. So it means that we can calculate the new solutions of the red cells in parallel. Right? We can calculate the new solutions of all red cells in parallel, because all the inputs are known already. After we calculate the new solutions of the red cells, we go on to calculate the new solution of the black cells. So the new solution of the black cells depends on the new solution of the red cells, but we already calculated the new solution of the red cells in the first step. Right. So now we can calculate all black cells in parallel. Right. So now the SOR is divided into two big groups, two big steps. The first step, we calculate the new solutions for all red cells in parallel, and then we goes on to calculate the new solutions of all black cells in parallel. Right. Because the number of red cells and the black cells are the same, so you can see that the workload is balanced in different steps. So this is a new implementation of SOR. It's called the red and black SOR. It's also the implementation of SOR in the code you are going to see in the lab, right? Or for the coursework too. Now, we want to calculate the cells in parallel, right? We want to use multiple computers to calculate the cells in parallel. So it involves the decomposition of the cells. For example, we have a 2D cell. In this case, I use two processes or two processors or two computers, right, to calculate the solutions of the cells in parallel. And we divide or decompose the grid cells into two parts. And the process 1 is responsible for calculating the cells in the left part, and the process 2 for the right part. Right. Now, when process 1 wants to calculate the solutions for this point, it needs to get data from 4 neighboring cells, right, according to the communication pattern. It's okay for these 3 cells because these 3 cells are allocated to process 1, so process 1 knows the value of these 3 cells. But it's problematic for this cell, right? Because this cell is located to process 2. It's maybe in another computer. So process 1 doesn't know the value of this cell. Therefore, it needs process 2 to send the value of this cell to process 1. This is where the communication comes about. Same for processor 2. When processor 2 wants to calculate this black cell, it needs to get the data about this cell from processor 1. Right. So in general, when a process needs to calculate the cells on the border or on the boundary between 2 neighboring processes, they need to exchange the data on the boundary cells. Right. So that's why there is a communication. The processes need to communicate with each other. In this diagram, we use a 1D decomposition, which means that we just partition the cell along 1 dimension. Actually, we can have 2D decomposition as well. For example, in this case, we partition the cells along 2 dimensions. It's divided into 4 cells, four groups of cells. And now, a process calculate a cell on the border, right? For example, want to calculate the solution for this cell, or let's say for this cell, right? It needs to get data from this neighbor and also from this neighbor. So a process may have more than 1 neighbors. For example, right? If we use a partition, right? Maybe it's a process may have 4 neighboring processes, right? Right. So that's for the decomposition of the grid cells. In this case, in our coursework, maybe 1D decomposition is okay because of the number of processes you can use for your coursework because the size of the cluster, basically. So 1D decomposition is OK for our coursework. Now, let's look at the main loop in the code. So there is a for loop, and T is the simulation time. So it starts from time 0, and the T end is the end of the simulation time. For example, I want to simulate for 2 minutes or 2 seconds of the fluid flow. Yeah?
You just said that the 1D decomposition is just as useful as 2D decomposition for what do you mean?
What I mean is that, so I will talk about the performance model next lecture. According to the performance model, actually, 2D decomposition is better theoretically, but it's only the case when the problem size or the number of processes is very big. But in our case, maybe we can only use 16 processes. So in this case, actually, 1D is better, shows better performance than 2D, actually, than 2D decomposition. So that's what I mean. 1D is OK for this coursework. So T end is the end time of the simulation duration. Right? And delta is the time step, because we said that we need to discretize the time. Right? And delta basically is the time step from one discrete time point to the next discrete time point. Right? But the problem is that the delta is not a constant value. So that's why in the first step, we need to calculate the approximate time step delta. The reason is because when we establish the governing equation, we said that we use the mass conservation. Right? In order for the equation to work stably, we need to make sure that the amount of fluid, or in one time step, the fluid flow across at most one cell. Right? If we allow the fluid to flow across more than one cell, which means that in one time step, a fluid flow into the cell, and then in the same time step, it will flow out of the cell again. So it doesn't make much sense, right? Because mass conservation means that in this time step, we need to calculate how much fluid flow into the area, and then calculate how much fluid flow out of the area. And according to the mass conservation, the amount of fluid flow into the area should equal to the amount of fluid flow out of the area. Right? So that's why we need to first calculate the time step. We just the code, we just look at what's the current velocity of the fluid, and then adjust the time step so that it will not flow more than one cell in one time step. Right? And then the second step is to calculate the tentative new velocity of the fluid. Right? It's not the final velocity, it's just tentative velocity. And then we use the tentative velocity to calculate the right-hand side of the pressure equation. Right? So B is the right-hand side of the equation. Right? So basically, it's to calculate the this vector. So it will use the tentative new velocity Fg and to calculate the right-hand side of the pressure equation. And then use the red and black SOR, which is the SOR we introduced earlier, to solve the Poisson equation, which is to calculate the pressure of the fluid. And then to update the real velocity of the fluid, and then calculate the velocity of the edge cells. So this is the main. These are the main steps of the code. Actually, each step corresponds to a function. in the code. In the lab session, you can take a look. Perhaps you can first benchmark the time spent by each function, because it may not worthwhile to parallelize every function. Maybe, for example, a function only occupies 1% of the time. Even if you spend a lot of time parallelize it, it doesn't affect the execution time of your parallel code by much. So that's the background of Coursework 2. Any question? Right, if not, I will talk about the requirements of Coursework 2. So what you need to do in general for Coursework 2 is that you will be given a serial program, which means that it can only be run on one computer. Right? It's a serial program. It's called common. You need to parallelize the common code and write a report. And 80% of the floor mark comes from the parallelization using MPI, and 20% of the mark comes from the parallelization using MPI and OpenMP. I guess Richard has talked about the difference between OpenMP and MPI. So OpenMP is used for shared memory architecture. For example, a multi-core computer, right? And these multiple cores share the main memory of the computer. So when one thread wants to communicate with another thread, they just write the data into the shared memory. And then the other process can get the data, the other thread can get the data from the main memory. The two threads achieve the communication. But MPI is for the distributed memory architecture. For example, a cluster, there are a number of computers, right? They don't have shared memory. So if two processes are located in two different computers, when these two processes need to communicate with each other, for example, about the values on the boundary cells. So one process needs to send messages explicitly to the other process, right, in another computer. So that's why we have different parallel programming paradigms. So because you're going to run your code on a cluster, right, which consists of a number of computers. So for the parallelization across different computers, you can use MPI, but a computer is a multi-core computer, right? It contains multiple cores. So for the parallelization across different cores in the same computer, you can use OpenMP. So you can develop a hybrid approach, combining OpenMP and MPI, right, which can achieve even better performance compared with the pure MPI approach. So the detailed requirement for coding is that you need to parallelize the common code using the pure MPI approach or a hybrid approach. And you need to profile which common function are more time-consuming. So basically, this affects your parallelization decision. Which function you want to parallelize, you should spend most of your time working on it. You need to design your decomposition strategy, so how you decompose the grid of cells among the processes. How you exchange the data between the neighboring partitions, and what MPI functions you are going to use. For example, are you going to use MPI collective operation or just the individual send and receive, etc. For a hybrid approach, obviously you need to add the OpenMP directives. You need to benchmark the execution time of your parallel code. So you have your pure MPI program or hybrid program. You need to benchmark what's the execution time of your parallel program over different number of processes. Also, you can change the problem size if it can help you to observe the trend, because if the problem size is too small, it may not show the full potential of your parallel program, right? So you can increase the problem size so that you can see a better trend as you increase the number of processes. If you develop a hybrid approach, you need to benchmark the runtime of the hybrid parallel program and compare the performance between the hybrid approach and the pure MPI approach. And this is very important. Right. After you parallelize the code, you need to make sure that the results or the solutions generated by your parallel program is the same as the solutions generated by the serial program. Right. Because we can't just, in order to increase the performance, we change the solution. Right? It's not tolerable. So the code needs to contain adequate comments to show that you have a good programming practice. The requirements for a report, so you need to develop the parallel program. Also, you need to write a report. Because you profiled the functions to determine which functions are more time-consuming, so you need to discuss the profiling results in the report. You need to discuss your MPI implementation. For example, what's your decomposition strategy? What's your load balancing strategy? Right. You need to balance the workload among different processes, which means that you need to partition the grid of cells evenly among the processes, right, or as evenly as possible. You need to discuss the strategy of exchanging the boundary data between the neighboring partitions. And you need to discuss the MPI functions, right, why you are using this MPI function, right, in your code. Because you need to benchmark the change in the execution time of your parallel program as you increase the number of processes, as you increase the problem size. Right? So you need to present the results in graph or table. You need to analyze and discuss the performance of your parallel program. So you present the results in graph or table. You should discuss that whether this trend is good or not so good, whether it's to be expected. Right. If you develop a hybrid MPI, OpenMP approach, you need to discuss the OpenMP implementation. Right? Benchmark the runtime of the hybrid parallel code and present the results. You need to discuss the performance comparison between the hybrid approach and the pure MPI approach. And also, you need to pay attention to your writing skills, right? But we will not be too harsh on the writing skills. As long as you don't have too many language mistakes, we will be fine with it. Up to 6 A4 pages. So 6 A4 pages should be enough for you to write all the discussions, right, of your code. After you develop your parallel code and you write your report, you need to zip it into a zip file and then submit it to the tabular. Right? The deadline is 16th of March. If you developed both pure MPI approach and a hybrid approach, you can put them into 2 separate folders. Right? But your report should be put at the top level directory in the folder. Right? So that's it for all the requirements for the coursework 2. Any question? Yeah?
So the number of MPI nodes that you have is variable.
You have, I think the maximum for the cluster, I think is 16 nodes. You can use. Yeah, that's the partition, CS42 Viper partition. Yeah. Yeah. Yeah.
What's the environment that with the has
Sorry?
What's the environment
how many, you mean how many nodes? Well, you can do some experiments about it, right? You have your parallel program, and then you increase the number of processes. You know, normally the trend would be, as you increase the number of processes, right? The execution time will go down, then it will level off, right? Even if you increase the number of processes further, the execution may not be decreased further. So this is kind of a cut point. You say that once you increase the number of processes to this point, no, you don't have to increase it anymore. You don't know how to, so you are not sure how many nodes you need to run the.
No, it's not like that. I don't know how many nodes you will test on.
Okay. How many nodes? Well, you don't have to worry about that, right? You just optimize the parallel program, right? And we'll test your parallel program to see that it can perform in a good way. Yeah. Any more questions? Yeah.
Yes. You said that the OpenMP part, the hybrid part, is worth 20% of the box.
Yeah.
And in this slide, you said if you develop the hybrid OpenMP implementation, that's why I'm kind of confused. Like, do we need to? Do we not need to? Because it's if you develop it, then.
Yeah. So, which means that if you don't develop the hybrid approach, you only get 80% of the full mark.
So you should do the final submission to be able to get 100%.
Yeah. Yes. Yeah. It's just the proportion, the weight of these two approaches. The pure MPI is 80%, and hybrid approach is 20%. Yes.
Are we supposed to have a separate pure MPI and MPI hybrid one, or are we
Separate. So if you develop both approaches, you can put them into separate folders. Yeah, in your zip file.
But you can't just do like just the hybrid. You have to do the pure as well.
Yes, you have both. Yeah, because you need to compare the performance between them. So you need to have two implementations. What time do we have? We have 3 minutes, so I just quickly go through the lab session instructions we are going to do in the lab session today. So this is the guide for this lab session, for the lab session this week, actually today. Right. So this trick, you need to load the MPI. Right. I think you have done that in last lab session. And so this is the command, how to run the command code. Right. Just type command. This is the executable code. And you can, so X and Y is the size of the X dimension and the Y dimension. Basically, you can change the problem size this way, right? Change the value of X and Y. And the T is the simulation, time duration, right? You can change the duration of your simulation as well. So by default, so I means that it will take an input file. By default, it will take common bin as input, right? And the output, by default, is also common bin. So it means that we have a common bin file. We have a common bin. We have a common bin, right? So this is a code, common. It will take common bin as input. Common bin basically contains the solutions of the fluid, which is the velocity and the pressure. And then after run the common code, it will write the solutions back to the common bin file. So basically to update, the new solutions. Right. So if you want to view the common solution, you can use bin2 ppm to convert the binary file into the image file, and then you can visualize the output of common. Right? And check the correctness of your parallel program. We said that the output of your parallel program should be the same as the output of the serial program. So this is how you compare them. So you use a diff-b to compare the output of these two programs. Right. One thing to bear in mind is that because common being take common being as input by default. So if we want to compare the output of parallel program and the serial program, you need to make sure that the input of these two programs are the same as well. Otherwise, the output will not be the same. How to change the problem size? We can change the value of x and y. And profiling the code, we said that you can profile which function take most of the time. You can use prof. In order to do that, you need to make sure that there is a PG option in the makefile, right? So when you add this PG option, when the source code is compiled, it will automatically insert some time benchmarking functions. So then, when you run common, this time functions will record the time spent by the functions, right? And then you use the gprof common. It will show the how much time spent by each function. Yeah, that's it. All right, see you in the lab session later.